Okay, so the last talk of the week is by Jan de Gier from Melbourne about limiting current distribution for a two-species particle model from first principles.
All right. Thank you, Filippo. And let me also start by thanking the organizer. Everyone thanks the organizers, but there is only one really, which is Filippo. So thanks very much, Filippo, for putting up this workshop. And thanks to everyone for being here on a beautiful Friday afternoon, Florence. So I want to talk about work which is stems from a similar program at the Kavli Institute in Santa Barbara, where we sort of started talking about this for the first time. And we got some results in sort of the following year, and there's a dirty version of the results in a PhysRev letter already in 2018. And the intent was always then to write it up more properly in a maths paper. And of course, you find out that there's lots of things that were done too dirtily. The results are fine, but to get it all properly done took another 3 years, and that's just recently being accepted. So this work is in collaboration with Seiying Chen, a former student in Melbourne, and the Japan group led by Tomohiro Sasamoto, involving 2 students, Yori Hiki and Masato Usui. And I want to highlight here that a lot of the details that were sorted out in the recent year were done by Masato. Okay. Yeah, so let me start by introducing KPZ. It's been talked about in other talks, so I just want to sort of set the stage a bit. So this is stochastic growth in 1 + 1D, normal to a surface, and it was numerically studied in the 80s by these people here. And the basic object is that you have a random height function that you'd like to study, and the way it was studied by these people was using a nonlinear stochastic PDE, which is called the KPZ equation, where the rate of change of that height function is given by a kinetic term, and then the growth term is given by this nonlinear term here, and you add white noise to it. And the claim is that if you do this, diffusion plus nonlinearity plus this space-time Gaussian white noise, then that correctly describes 1 + 1D surface growth. That was experimentally tested in Japan, actually by Takeuchi, as was mentioned this morning. And he has actually a lab at the institute that Tomohiro works. And so when I visited Tomohiro, we just walked over to Takeuchi in this sort of setup where he studied liquid crystals, where you can study the growth. And I think it was Alessandra showing some stills of the videos that they produced, studying the height profile. And as we all know, this KPZ equation, or this nonlinear growth, produces non-Gaussian fluctuations at the interface. So the height profile grows linearly on average, so it's deterministic, and then the fluctuations are of order t to the 1/3. Theoretically, this was studied earlier on by a transformation to stochastic heat equation. So you just take the exponentiate height to get the function z that satisfies what is called the stochastic heat equation, and then there are results that look like the following. If you take the moment generating function of that function z, say at the origin as a function of time, then the expectation value of that moment generating function can be written as a Fredholm determinant with an airy kernel. So depending on the airy kernel basically looks like this. So there's a product of airy functions inside, and then some function f depending on the specific type of objects that you study. So once you're at this stage, you can then further do asymptotics for large time. And one of the sort of fundamental results here is that the fluctuations of that stochastic heat equation are indeed of KPZ type, meaning that if you study the height profile, you subtract sort of the boring deterministic growth, which was linear in time. So here I've sort of normalized the velocity to 1. Then this object fluctuates at the order of t to the 1/3. So if you divide that out, then this converges to a number, and the probability that that number is less than some given number s is given by the Tracy-Widom GOE distribution of random matrix theory. Right, so there's a lot of theoretical work behind the scenes here, of course, but this was sort of a very important result that several people in the audience have contributed to. So this is in the context of the KPZ equation, stochastic PDE, but as we know, this sort of phenomenon also occurs in the exclusion process. And just to give a little bit of history here as well, so we've seen the asymmetric simple exclusion process several times already. So you have a bunch of particles, and here I'm on the infinite line, and they hop around. So there's a hopping rate to the right, rate p, and a hopping rate to the left with rate q. Particles cannot occupy the same site. So that's the exclusion bit. And you can write down a simple Markov chain equation. So if p denotes the probability to see a particular configuration u at time t, then the rate of change of p is given by this Markov chain. So it's just all the rates into p give a positive contribution, and then if you're in t at time t, you can hop out of it, and that gives this negative contribution here. So this is a balance equation, and that just gives the rate of change. And you'd like to solve this equation for p with initial condition that at time 0, the configuration u is equal to the starting configuration mu. So at time 0, this should reduce to a product of delta functions. That problem was solved by Tracy-Widom, and it's like a Bethe-Ansatz type of calculation. So if you just look at one particle, it moves with a Bethe-Ansatz type of eigenfunction. So I've written it in this particular way. So some function of a auxiliary variable z, some essentially complex variable z, to the power when u is the position of the particle, times an exponential that depends on t, and then this is a rational function also depending on z, which is basically the eigenvalue of the one particle process. And there's some parameters here. So p and q are the hopping rates to the right and to the left, and this tau that appears here is just the ratio of those two hopping rates. So that's a one particle eigenfunction. Of course, you want to know the multi-particle eigenfunction, and it's a standard Bethe-Ansatz type argument that the multi-particle eigenfunction for an integrable system, which this one is a product over the one particle eigenfunctions. So nu and mu are positions. So this is just a difference of the final and initial conditions, times a deformed Vandermonde type product, which are the scattering matrix elements, if you like. And then you have to take, you have to sort of symmetrize this. So you take a big sum over the symmetric group, where you symmetrize over all the positions of the particles. So this is the eigenfunction of the multi-particle exclusion process. It's the same eigenfunction as the XXZ spin chain, because these two models are very closely related. And to satisfy the initial conditions, so normally when you think of spin chains, you put this model on a ring. You have this Bethe-Ansatz wave function, and if you put it on a ring, that imposes some conditions on these complex variables z, and that gives you the Bethe-Ansatz equations. Here we're on an infinite line, and we're not satisfying cylindric boundary conditions. We have to satisfy an initial condition, and that is done by integrating over these variables z. So instead of imposing Bethe equations, I'm now going to integrate over them, and I need to put in a certain factor here to make it all work. And if you do it in the right way, where these are contour integrals around the poles at 1 over tau, sorry, the poles at negative tau, this at t equals 0, where this exponential disappears, gives you the initial condition. just by residue calculus. Okay. So that is the Green's function, or the propagator, or the transition probability, whatever name you want to give it to in whatever area you work in. You want to use it to compute observables, and for RCEP there's a useful one that gives nice results. So for example, you're interested in the current, the flow of particles, which is this nxt. So this is the number of particles to have crossed a given site x after time t. And you'd like to know, yes? No. It's an interacting, non-determinantal, no. Well, so this is not a determinant. So if it was determinantal, then this sum over the symmetric group would be the expansion of a determinant. It's not, no. Because you have Zi minus Zj here, so it doesn't factorize in the... not in the way it's set up here. So yes and no, I would want to say. So in the spin chain, for example, you can take the anisotropy parameter delta to 0. You get, but that's not a natural limit here. And what you can do is take a tacit limit where you set one of the hopping rates to 0. So now particles can only move to the right, but no longer to the left. That's not determinantal, but it's very close to being determinantal. So, okay. Yeah, so going back to a physical observable, it's like the flow of particles at a particular site. So you'd like to know the expectation value of this. So as written, that the mathematics of it doesn't give you a nice answer. What you need to do is the following. You take tau to that observable, so tau to the power nxt. Tau was the ratio of the two hopping rates. And then I take like the space derivative, the discrete derivative, q of x minus q of x minus 1. And I call that q tilde. So that is like tau to the power n at x minus 1 times an indicator function that there needs to be a particle at position x at time t. So that turns out to be a convenient quantity to measure. And if you go through the maths, you'll find that the expectation of a product of these q tildes, so this is a k-point correlation function, is given by this multiple contour integral with the q van der Monde type factors, product over the eigenfunctions, and then just a very simple factor that appears here. And the reason this works is that this is actually a duality. So someone spoke, Chiara, about duality before. This is actually a duality because these qx's, you can interpret these as a k-particle system, and these correlation functions evolve according to a second k-particle RCEP. And then the solution of the equations of motion for that process is just this same beta type of function. So that's why this sort of particular form is useful. But once you get this nice, I mean, this is a nice formula. So it looks a bit involved if you haven't seen this before, but for those who work with multiple contour integrals, you can see this is a really nice one. It's fully factorized aside from this van der Monde type factor, which you always have. It's fully factorized. And so from here, you can compute asymptotics, like you want to let t go to infinity, and often also k should go to infinity. And that can be done, and out of this, you can again find that if you look, for example, at the origin, the net number of particles crossing the origin at time t is again, well, the leading part is deterministic in time, is linear in time, so you subtract that, then the fluctuations are of the order t to the 1/3. So you divide by that, this converges for large time to a number, and the probability that that number is given in some fixed number s is again given by this GOE random matrix type of distribution. So the same as for KPZ. So this is in the same universality class as KPZ. So this is what's called KPZ universality. Yeah. 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 Yes, correct. Oh, yeah. So you're right. Yeah. Yeah, you're right. So and this is the surprising fact, of course, that for some limiting results, indeed you find distributions that also arise in determinantal processes, even though you're dealing with an interacting well, yeah, I don't know. It's not integrability, right? This is supposed to be a universal result. So even non-integrable models will have that sort of behavior. And okay, but anyway, so maybe because I want to, in view of the time, I want to continue. But we can talk about this for sure. It's very interesting. Yeah, yeah. Okay, so this was all a background. Oh, sorry. So the different values of tau is sort of hidden in this velocity here. Well, I've fudged a few constants here, so yeah. But just for clarity of the presentation, but yeah. But essentially the behavior doesn't depend on tau, unless tau goes to 0 or infinity. Then, but even then, I think it's sort of the same. Yeah. So the ingredients of this were that there's a Yang-Baxter integrable stochastic lattice model, so that allowed you to write down a multiple contour integral expression exactly. So observables are expressed in terms of such k-fold integrals using techniques that are very similar to Bethe-Ansatz. Then you'd like to know asymptotics for large k, and for that you need to sort of transform the problem to a Fredholm determinant in which k appears as a parameter, a free parameter. You can analytically continue and then do a saddle point analysis, and you get these distribution functions out of it. So I didn't show that last bit, but I will in the rest of the talk. What this talk is going to be about is a rank 2 model. So now we're going to deal with 2 species of particles. Excuse me. And the main difficulty, there's added technical difficulties that you get. And so for experts, already you can anticipate that you have to do something like a nested Bethe-Ansatz here, and that will give dynamic poles in the integrations. And so the asymptotics becomes much harder because you have to somehow manage moving poles rather than fixed poles. And we'll see that it can be done, and you get a combination of Gaussian and GOE modes in this 2-particle model. Okay, so I'm going to talk about this bit. So one obvious generalization is if you think about the asymmetric exclusion process, it's very closely related to the XXZ spin chain or the 6-vertex model. So that's arising from UQSL2, and so you can think, well, for multiple species, I should take higher rank UQSL3 R matrices, for example. And that can be done, and a student in Melbourne will talk about that next week. I'm going to talk about another 2-particle process, which is introduced by Arndt, Heinz, and Rittenberg in the 90s. And that's this model. So the plus and minus particles, the plus particles just move to the right, stochastically. And the Q particles move to the left. So if you have 0 minus, then the minus hops to the left. And if they are adjacent, they can interchange place if the plus is to the left of the minus. But they can't go back. So if the minus is to the left of the plus, they can't interchange back. And so in terms of world lines, The purple trajectories here are the trajectories of plus particles. They start here and they move to the right, and the green particles are the minus particles, and they move to the left and they cross in the middle, but they can't cross back. So after some time t, they will have all crossed. And we're interested really in sort of the middle region here, and understanding the fluctuations that are around here, where you have plus particles, minus particles, and empty space, right? So there's okay, so you can, there's this sort of heuristic theory, nonlinear fluctuating hydrodynamics, or there are other names for this, where you start with a continuity equation for a two-component gas of particles, where U represents the density, two components, and J is the current, and then you can analyze this by taking sort of a mean field approach here, and there's a technical reason that I can do that in this particular case, and so the currents in terms of the densities of the plus and minus particles are given by such expressions. So then you can add diffusion and noise as you did in the one component case, and you get a heuristic nonlinear fluctuating two-component KPZ type equation, and you can analyze that in a physics hydrodynamics way, and that leads to a prediction that the crossing probability, when you have the two families and they cross, on the picture that I showed before, that probability is given by a product of a GOE distribution and a Gaussian distribution, where S plus and S minus, the arguments here of these distributions, are some eigenmodes of this two-component system. And the aim of the work that we've done is to actually rigorously prove this approach, that this actually works. So this is really very hand-waving. So it's the probability that after time t, the two families have completely crossed. Yeah, and then you want to sort of sit close to when it has just happened to see the fluctuations. Yeah. And so to analyze this, we first write down the stochastic Markov chain master equation as I showed before for the one species case. So if G represents the transition probability or the Green's function or the propagator, then its rate of change is given by the sort of hopping of the particles. And this is for a free evolution, when all the particles are well separated, and the interaction between particles can be taken into account by imposing certain boundary conditions. So it's very similar to coordinate beta ansatz, if you're familiar with that. So we can do exclusion, we can do exclusion for the minus particles, and then we can do the interaction between the plus and minus particles. So you just get some conditions on the function G, and also we need the initial condition. So again, there's no sort of periodicity or cyclic condition. We need to impose an initial condition. But because this model is integrable, you can do all of this, and you can write down an explicit form for G using a slight generalization of beta ansatz, and that is written here. So my claim is now that if I take at time 0 all the plus particles whose coordinates are x to the left of all the y particles, of all the minus particles whose coordinates are y, and in a final condition that all the particles families have crossed completely, so now all the x's are the final coordinates of the plus particles are all to the right of the y coordinates, then the transition probability from the t equals 0 case to the final case is given by this expression here. And I just want to highlight a few things. So we're now integrating over two families of auxiliary variables, z's and w's. So this is a reflection that you have two families of particles. For the plus family, we have this determinant, which is like it. So it's almost a determinantal process because I take a particular limit. But this is more or less the single species ASAP transition probability. So this is Schutz's formula. And of course, for the minus particles, it's the same formula, but the only difference is that they move in the opposite direction. So that's just a change of coordinate system. But then they interact, of course. So if I wouldn't have any interactions, these families would just move through each other without seeing each other. Then it would completely factorize into these two transition probabilities. But there is an interaction which is described by this factor here, and that's for each crossing of particles. There's a 1 over qz plus pw, where z is the momentum of the plus particle and w the momentum of the minus particle. So every time a plus and a minus particle cross, I get such a factor. So if all of them completely cross, I just take a product over all of these crossings. We can write down similar formulas for partial crossings. It just means that this doesn't become a complete product, but you just take a product over the ones that have crossed and not the ones that haven't crossed yet. But this is of course much easier to analyze. And there's this time-dependent factor. So the time dependence enters here with lambda, the eigenvalue of the transition probability matrix, and that is given also in terms of z's and w's. Okay. So now we want to use this, for example, to compute this complete crossing probability. So let's start from an initial condition where we put all the plus particles to the left of the origin and all the minus particles to the right of the origin. And then we let the system evolve, and eventually all these two families would have completely crossed. And then I'm summing over all the final coordinates of where they can end up. So all these sums have to be performed over the final coordinates, but they can be easily done. They are all geometric sums in terms of this transition probability. So that is basically the probability. And when you do this, you find something surprising, namely that after doing that and some further massaging, this probability can again be written as a multiple contour integral, but now the kernel is completely factorized. So here, in the transition probability or the Green's function, there was no factorization. We had determinants here, which is nice, but it's not factorized. And in more general models, you don't have determinants. But when you sum over the final coordinates and use some symmetrization identities, this particular quantity, where the leftmost particle has crossed all the minus particles, so the two blocks have completely crossed, you get factorization. Yeah, I suppose you must have. We haven't. Yeah, so we get that. Yeah. So I just want to emphasize again here that we have that interacting factor. So I'm doing all these integrations, and you could attempt a naive asymptotic approach using saddle point analysis, were it not that the z's and w's don't completely factorize. So you have this sort of interacting term. So when you want to sort of analyze the asymptotics for the z's, using, say, steepest descent, w's appear in there. You still need to integrate over the w's as well. So that complicates matters. So all the poles are around the origin, but the e to the lambda produce an essential singularity because there's this 1 over z and 1 over w, so you deform your contours to lie around other poles, and then you can further analyze it, and then some of the poles in the w's are simple, which you can actually evaluate, and you get do the w integrals and find this. And now the interaction has disappeared, and basically you get a single species exclusion process back. And so there's a corollary: when the numbers of particles are the same, you get a single species TARCEP back out of this. And that is sort of obvious, because when we take this initial condition, and we should think of that the number of plus and minus parts becomes asymptotically large, essentially all these zeros here disappear, and I just have pluses and minuses, and that's a single species particle, where the pluses are the particles and the minuses are the whole. So I'm not actually doing something new, right? But it's sort of good that at least that in that limit we get back what was already known. And so from here it's sort of a good exercise to do this anyway, because you can practice the analytic asymptotic calculations to indeed get out the GOE distribution. So more interesting, and I think this is what you had in mind, Andrea, is where you take a random initial condition in, say, the plus particles. So this is Bernoulli distributed at time 0, and maybe a step initial condition for the minus particles. So now this is genuinely a rank 2 or 2 particle model. But again, we can analyze this, and the probability that with this initial condition all the families cross, again, nicely factorizes. So the kernel of your integral nicely factorizes, and the randomness appears as an additional pole here, where rho prime is just the parameter associated to the Poisson distribution, the exponential distribution of your of the particles here. So there's an additional pole that you need to take care of. How am I going? Yeah, okay. So, so this is the initial condition here, and we want to evolve this in time. And because we have a random distribution of plus particles, you can already see that this is only interesting if the number of plus particles is less than the number of minus particles. This leftmost plus particle is further away from the origin than the rightmost minus particles. So I need to take more minus particles for them to sort of, if I'm looking at the origin, and if I want them to cross at time t near the origin, the number of minus particles needs to be larger than the number of plus particles. And it's sort of, once you stare at this formula long enough, you actually see that if the number of plus particles was larger than the number of minus particles, you get something non-trivial. If it's the other way around, you can actually evaluate this very quickly, and you get again single species models, because you're looking at a time where the minus particles have already disappeared, and you're only looking at the plus particles crossing the origin in this case. Okay, so then the asymptotics. So we want to think of the particle numbers growing in time linearly, and then they fluctuate on the order of either t to the 1/3 or t to the 1/2. So these alpha, beta, gamma, delta are predictions given by hydrodynamics. So we want to, that what you can do is sort of confirm these predictions, or we take these as sort of unknown parameters that will be fixed self-consistently when you do the steepest descent asymptotics. And then you need to analyze expressions like this, that the probability of total crossing is a n times m-fold integral over a factorized integrand, where n and m are going to be very large. So that looks undoable, but there is this nice trick in this model that everyone uses, that if you can write this as a determinant, which you can, in this particular way, then you can reverse A and B. So this is just linear algebra. The determinant of 1 minus AB is the same as the determinant of 1 minus BA. But whereas A times B, if you can find those matrices AB such that this is a finite matrix, so in this case, this is just becomes an m by n determinant, if you like. Once you swap it, it becomes an infinite determinant or a Fredholm determinant. So that doesn't look like progress, but the important bit here is that these numbers m and m appear as parameters now inside B times A. And so they just become parameters, and so you can actually think of taking this scaling limit once they're inside this Fredholm determinant. Whereas if they are dimensions of your matrix, then it's much harder to do this. So then you don't actually know what to do. So that's the trick. And then, of course, there's still a lot of work involved. And so here's the work, and it's the last 5 minutes. So yeah, okay, but it's Friday afternoon. So, I don't want you to sort of fully absorb all the details here, but I did want to show these slides so you have some appreciation of what is involved in pushing the analysis further. So there are integrals of this form that you need to do. So you have this Fredholm determinant here, which itself is a reasonably complicated project, but it depends on n variables z, which you then need to still integrate over outside the determinant, possibly with some other function. And the kernel of this Fredholm determinant looks like this. It's a combination of two one-dimensional integrals, one over zeta and one over w. So that's not too bad, two one-dimensional integrals. But the integrands are factorized. There's some functions f and g, but these are also factorized. I didn't write them explicitly. But inside here are all these z variables that you integrate over outside. And there is this factor here at the end that depends both on w and zeta, so on both of the integration variables. So it's still not entirely straightforward. But then there is an important observation here, is that if you analyze this Fredholm determinant, basically this is a series over determinants of k, of finite subsets of k. So you can analyze determinants of k, and then you find that if you integrate over that, there's a particular structure that allows you to write this k that depends on all these z variables. You can take that out, so there's a contribution that does not depend on z, and then is actually. So I'll take that back. So if I have this determinant that depends on all these z variables that I'm integrating over around the point 1, where there's a pole. And what you can show is that there is a pole-free part, which you get by setting z equal to 1, that you can take out, and then the remainder is just depends on z minus 1 times some other functions. And since you're integrating around z equals 1 of all the zi equals 1, this bit is small, and but that's a very sloppy remark, of course, and the hardware goes into showing that that's actually small. Right? And I'm not going to talk about that because that's really very technical, but the upshot will be that the integral, that complicated integral, can be approximated by setting all these z variables equal to 1, in which case the outside z integral just needs to be taken over whatever was outside, and this bit no longer depends on z's. And then there are lower order terms, and we can show that these lower order terms are actually small. And once you get to this stage, then you can continue with a scaling ansatz and rescale the kernel. And so here you can see this is in a form where you now take steepest descent type of approach to approximate integrals like this. And you find that well, in the usual way, for particular combinations, you'll get that the second order Taylor expansion vanishes, and you get the third order, and that's how you get the KPZ scaling exponent. So just to picture, to show you the type of contours you need to take to ensure all sorts of expressions converge uniformly. So it's quite finicky. Do you have a question? No. When you do these calculations in the complex plane, you have to really be very careful on which type of contours you integrate to ensure everything converges uniformly, but it can be done. And then finally, we end up with the theorem that the original discrete type of Fredholm determinant, which we get from the integrable lattice model, if you take the limit t to infinity can be taken by rescaling, and you get a continuous Fredholm determinant, and that you can interchange limit and determinant, so you can take the limit inside, and then you get the determinant of 1 minus the Airy kernel, and that then gives you the random matrix Tracy-Witham distribution. So that follows for this particular model, and we get that this type of integrals over these determinants, they converge to a product that involves a Gaussian and the GOE distribution S, where S is an eigenmode of the system. And so for example, S is this combination of the number of plus particles times a coefficient, the number of minus particles times a coefficient, and then T times a coefficient, divided by T to the 1/3. Right, so this is some particular combination of the N, M, and T that divided by T to the 1/3 that converges when T goes to infinity. So if you look at that scaling limit, you'll get out these distributions. And so this is my last slide. The final result is that for that crossing probability, starting from the lattice model where we had an exact expression for this and doing all the asymptotics and all the analysis, you get this product of a GOE distribution and a Gauss distribution into the eigenmodes. And the eigenmodes are very explicit. And one fluctuates on order T to the 1/3, giving the GOE distribution. And the other mode fluctuates at order T to the 1/2. And that gives you the Gaussian distribution. And then you can sort of make plots like this, and yeah, it all works. Okay, so this works, sort of the first proof or rigorous analysis of a two-particle mixture, two-family mixture, showing that heuristic theory indeed does work, the sort of more naive hydrodynamics approach. Of course, we use integrability, and we find this mix of Gaussian KPZ modes. But the main point is these dynamic poles in the integrand. And so also if we go higher, even more families of particles, this will only get worse. So if people have experience with how to deal with dynamic poles, or when you integrate over multiple families, then I'd be very interested to learn from you. All right, thanks so much.
Thank you. Any question?
Is it possible to think of the final result in some sort of interpolating way? Maybe there's an extra parameter such that when you tune it one way, you get GUE only, and the other way only Gaussian? Like this, well, you don't really see it in the product, but perhaps in the model there's some...
Yeah, well, there isn't. I think in the general theory, when you set up the hydrodynamics, you can think of that way, where you have two eigenmodes, and when they become degenerate, it could be only Gaussian or only KPZ or something else if they degenerate. Yeah. So this, in principle, could happen. In this particular model, we don't see that happen. I think one of the predictions is that you always have a one direction where you have KPZ type fluctuations, and then all the other directions are generically Gaussian. Yeah.
So there is not a regime where you can observe both KPZ modes? Or...
No, I don't think so. I think
okay, no, I was asking because I've been using nonlinear fluctuating hydrodynamics also for a multi-species particle system, and so if you play with the asymmetry, for example, you can recover Gaussian, KPZ or Gaussian, or KPZ, KPZ. So it cannot happen in this. There is no modification of this model or
so I think in the hydrodynamic setting, there is a classification like that, and it is you have one KPZ direction and the rest are Gaussian.
So you can, in this case, you can only observe
unless you
KPZ.
have a degeneracy. If you have a degeneracy, you might get other things.
Okay.
Like quartic one, yeah. So we have 1/2 for Gaussian, 1/3 for KPZ. You can get 1/4 if you have degenerate cases, for example.
So one quick question was, you had in the AHR model, you have P plus Q equal to 1. Yeah. If you relax that, is there any hope of this working?
Yeah, you can. You can. You should talk to Luigi and Tomohiro.
Okay.
They are looking at this. Yeah.
Okay. And the other thing I wanted to ask was about your last point. I mean, you know, there's Craig Tracy's former student Jung-Hyun Lee has computed using Bethe-Ansatz multi-species probabilities where you have, if I remember correctly, you have one first class particle, one second, one third, and up to n, and he computes the probability of going across the origin.
Yeah.
Does his kind of strategy generalize?
Yeah, it does, and you should go to Will's talk.
Yeah.
Will, if you put your hand up. So yeah. Will talk about exactly that, where we will do blocks of particles in the higher rank generalizations of RCEP. So the SLN type models.
Okay.
But not where you have single particles, where you have a macroscopic number of each of the family of particles, and they interchange. So very similar results. Yeah.
Thanks.
But we haven't done the asymptotics for those results.
Yeah, sorry, I'm not sure if it's a good question, but you said the other directions are Gaussian. Can you prove that with your techniques, the Gaussian fluctuation, and can you calculate everything in these other directions? Yes.
Yeah. Okay. Yeah, we can calculate I mean, it's not always easy, but we can.
But you can do it. I mean,
you can calculate everything, and actually the Gaussian part is sort of simple because you're basically the Fredholm determinant approach fully collapses. It just becomes like a zero-dimensional Fredholm determinant. Immediately it's the Gaussian. Yeah.
Just a very naive question. When integrands factorize, then there is electrostatic interpretation of all of this as a system of two charges on circles in a complex plane. Does it help to analyze various phases or dependence on parameters?
I'm not sure I understand.
Just this integral. Yeah, let's take this integral, put it in exponent. There will be a system of two charges in a complex plane with logarithmic interactions. So does it help to see what the phase space of the system is as a function of parameters?
It's sort of what we do with the
it's not absolute.
It's sort of we take this steepest descent approach. So it's sort of at the end of the day, I guess, if I understand correctly, that's what you do here.
Okay.
But
so,
so superficially, I would say no. We haven't done like the log gas type of analysis, but I think on a deeper level, it's sort of equivalent to what we've done.
Yeah, so from nonlinear fluctuating hydro, there's a kind of an easy argument to say it's KPZ and all that. So do you see some bits of this hydrodynamic argument in your calculation? Or is it like just technically completely different? Because in the hydro, I mean, you take saddle point essentially and all that stuff, right?
Yeah,
So.
yeah. It's very involved. And I'm sure at one day this can be done in a maybe quicker way or more smooth, and it's sort of insightful. But it is true that when you start from expressions like these integrals, that here it's not obvious at all. But when you do all the transformations and then do steepest descent, the scaling limits that work, they pop out in a self-consistent way of the steepest descent approach. So what you get out of hydro, you don't have to take that as input. Within a self-consistent approach here, the same scaling limits as the hydro ones come out. Why that is the case, or that's, I have no good intuition. Yeah.
How do they come out from exactly like that? I mean, that's how
Yeah. Yeah. Yeah, so there must be something similar, but of course here the calculation is much more involved. But yeah.
Other questions?
Yes. So here the duality function, basically the identity, because we're just summing over the, so let me go back. So normally if you're interested in a duality observable, you would insert it here and then use the propagator to then evolve it in time according to the dual process, and then maybe sum over the final variable. So here there is no duality function, because basically the duality function uses the identity. It is possible, and I'm not sure if Will's going to talk about it, to do exactly that for the other multi-species models. So, but this is work in progress.
Okay, thanks.
Just some remark concerning the question by Sasha. So it seems that indeed there is something as Coulomb gas, and there will be pairs of charges which are made by several poles when you start to do these integrals. Is it correct? I mean, a la Corvin and Borodin.
The way we analyze the asymptotics is we first do lots of manipulations, and then we end up with one-dimensional integrals. So it's probably the case, but we haven't looked at that.
Maybe this another way of evaluating the integral, when you expand the contours and you pass through all the poles and you obtain these bound states of charges.
I see. Oh, okay. So no, we've not done that. We have not followed that approach, but maybe it's it's a good suggestion. Yeah.
Other questions? If not, let us speak again.